solid and containing the interior point. That is called 2-simplex, and tetrahedron is 3-simplex, like that. But mathematically we can just say that okay, this is the definition. It should satisfy this condition. The convex hull of n plus 1 many points in general position is called like n-simplex. Otherwise we know that if we are given finite set, then the convex combination of the finite set is like convex hull. Right? Okay, so this is the definition. So definition, if we do little bit geometry, so this one zero-dimensional things we can consider. So these are like tetrahedron. So definition of n-simplex, okay? Okay, why n-simplex is important? Because we can see tiles everywhere nowadays. So if you see the floor, we have tiles. So tiles is like rectangular kind of things, but you can make it triangular. So if we are having some object and locally we want to know, so how we should, what will be the best process to know the manifold, right? Locally or globally. Locally, if we can fit something very nice, so what is the nice object? This is the nice object. So we fit it together so that it will be covered by these tiles, right? So tiles means this n-simplex. And that kind of things is called like simplicial complex. So we will define that simplicial complex. So it is nothing but it is a collection of n-simplices or any dimension, 0 dimension to some n-dimensional. If it is finite dimensional, it should satisfy some property. So that means the overlapping should not be like this. It should be like in the boundary. Otherwise, if it is overlapping in a bad way, then we cannot do the calculation. Right? We cannot say that, okay, how much overlapping is there. But if it is overlapping very nicely, then we can say that, okay, its property is calculable. Like we can do the computation using that. Okay. So this definition, okay, maybe many of you didn't see, so I will pause for a few seconds. Maybe one example is good. So I will go back and forth. So what it is doing, this triangle and this edge. So if we see the intersection of this, it is a face of both. So here, if we take this triangle and this triangle, so they are intersecting along this edge. So if it satisfies very nice properties like these tiles, then we say it is a simplicial complex. Okay. It's okay? But the mathematical definition is this. You know, what I feel in mathematics like is good because whatever we observe, we try to fit in such a way that we can apply it in many places. So we have some observation, putting the tiles together, we made like, and we know English because our ancestors were like quasi-British, so we know English. So we just write some English sentences, meaningful English sentences. Okay. It's okay, definition of simplicial complex. So we just need to remember that tiles are putting together very nicely. That's the simplicial complex. And if we do it, it will look much more nice. Okay. So what can we see from here? Suppose nowadays what we see wherever we go, some like a sculpture will be there, which looks like this. So you can thicken it. So homotopically, it's the same thing. As I told you, whatever I see is like topology, nothing there. And now my friend from analysis, they may say that, oh no, you need to give the exact map. Okay, we can give it, but for the time being, we are not interested in that. How the time is going. Okay, we have time. So now we'll have interesting concept. It takes time to digest the meaning of simplicial homology, but I will try to go very slow. All of us, we know ring, concept of ring, right? Or module. So what we have, this is a simplicial complex. So what does it mean? It is a collection of simplices which satisfy some condition. Okay? Okay, so we take this I-dimensional simplices, we just consider them as a like variable. So this AI, and we take the formal sum. What do you mean by the formal sum? It runs over all the index where the index set is finite. Now if we consider this like, okay, if it was finitely many, x1, x2, xn, we could take that summation of xi. So it looks like linear polynomial. So this is nothing but like linear polynomial kind of things. The coefficients is coming from some field. I mean ring. Here is a ring or field, whatever you assume. So this sum finite. This is a finite sum. So it makes sense, right? We should be clear about that. Is it okay? So what structure it is having? It is having a ring structure again. So given a set, we can take the formal sum and the set of elements, because if we add two of them, then again it is a formal sum. So, and if we, okay, multiply by the ring element, it is again there. So it satisfies the condition of the group. Okay. So this group is called like chain complex, ith chain complex. Okay. So I is coming from the dimension of this simplex. So what does it mean? So n-Simplex, we had n plus 1 many points which are in general position, meaning that if we take n many points from there, they don't belong to the affine hyperplane which has dimension less than n minus 1. Okay? That is the definition of general position. So is it okay? The chain complex, ith chain complex, that was very easy. So we just took the set of all I-dimensional simplices from this collection. Then we made the formal sum. That's easy, with coefficient coming from this V. And we said that okay, we will take this one. That is called ith chain complex. Okay, so what we can have from ith chain complex? Now look at here. So if we have a simplex, then it has a boundary. So boundary consists of faces, right? Those are like, again, codimension 1 simplices. But how many boundaries are there? If we are having n simplices, then n plus 1 many boundaries are there. So we should have a orientation on that set. So this is A is I simplex. Okay, so this is I simplex. Now how many facets will be there? I mean codimension 1 facets. So if we omit one of the vertex, then we will get all the facets. So how many will be there? I plus 1 many. Now what should be the connection between them? So the connection, the relation among themselves is given by this relation. So if we say boundary, we could say that, okay, we take the sum, but it will not help us. Because if we take the sum, it will not be interesting. So what we take the alternating sum. So first we have to consider one orientation. Since we take the finite simplicial complex, we can give an ordering of the vertices of the simplicial complex, which will induce an orientation on each simplex very nicely. And then we can have this formula. Is it okay? So like boundary map, the composition is 0. Because if you apply the boundary here again, then you have to omit some elements from here, then ij, so some calculation is there. It will say that the composition is 0. So that means zero, then you have to be like that. Like that. Okay, that's a good question. I like it. You know, a question should come. Okay, that when we were in high school, we loved to do problem solving, so many problems. But when we come to BSc, then we feel, oh, we did too many problem solving, we don't want to do. When we come to MSc, it becomes more or less. I don't know why. for me it become more and more because I didn't know many things. But students follow that, okay, I don't want to do the calculation, but here let's do some examples. So we take the boundary of 2 simplex. So it's like triangle, boundary. So it has 3 vertices. So what will be the 0, 10 complex? That will be generated by only 3 vertices because 0 dimensional. Okay. So and the 1/8 10 complex will be generated by the edges. So these are the edges. So now you can see we took the oriented edges. So this C1 is isomorphic to Z cube. Z cube means 3 generators are there and over Z. Okay, here the ring we are considering, that is Z. So it doesn't need to be filled. Okay, why this is trivial, why this is 0? Because in the boundary of triangle there is no other higher dimensional simplices. So the chain complex automatically it becomes 0. So the chain map, it will be like, if we just know this map very well, then we can get it. So what is this? So if we take this one, so by definition, okay, now the question is what it has to be, whether V1 plus V2 or minus. So if we take this plus, then the composition will not be 0. So therefore it is like if and only if. Some other coefficient, if we put some other coefficient also, like 2V1 minus V0, then also the calculation will say it is not 0. So therefore that is the if and only condition to have that composition of this boundary map is 0. So what will be V0 then? It is image of delta 1. So what is the image? Image is generated by these differences. So if we check, if we add these two or subtract these two, then we get this value. So these 3 are not independent, so they are dependent. And 2 of them, they are independent. Okay? As a module, they are like module basis, they are independent. So it is 2-dimensional subgroup of.
Why should the composition of boundary?
So if yes, 1-dimensional object, if it satisfies this one, so if we have that, then we get this one. Now we will have this relation. Now we can easily check that from here what should be the value of L. So M has to be equal to L, N has to be minus L, so this minus sign automatically comes. So because of that we have to take the alternative. So that's like sometimes you can run it. Okay. So any one cycle will be looking like this. So that means the one cycle is generated by this one. And what is V1? V1 is coming from image of C2. Right? But C2 we know that 0. So if we have a 0 module to some other module, the image will be always 0. So V0 is 0. So the quotient is 0. And other homology is like 0 because the cycle, okay, that quotient is like 0. Okay, so that is the computation for the homology of Sarkar. And we can see it takes some time to do the calculation. Now if we have to do some little more complicated things, so that natural question will come, what is the homology for n-dimensional sphere?